Okay, guys, thanks. So I'm going to talk about something a little bit off topic, but it's something that I find super, super interesting. I hope you guys too do as well. This talk is going to be a little bit theoretical. The things I'm going to talk about don't truly exist. They're algorithms that exist in academic papers, but this stuff does not exist yet physically. So we're sort of safe for now. I hope that I explain this stuff well enough that you have sort of an epiphany moment, or at least an oh wow moment. I hope to blow somebody's mind during this talk if I have. I've done my job successfully. So my name is David. I have a PhD in experimental particle physics. I'm now a recovering academic. I work for a startup here in Milwaukee called Scanalytics. So this stuff I'm talking about isn't directly related to what I do day to day. Oh, thank you. I wasn't sure how much I was projecting. Yeah, so I studied this stuff for a little while I was in school, and it really hit home for me, like this is something really, really cool. So if you guys want the speaker thing, here it is. I will come back to it at the end of the presentation again when we do Q&A. So don't worry about if you don't get it right now. Okay, so let's talk about communication. We've had a lot of talks so far, encrypting data at rest, encrypting data under various circumstances. What I'm going to be talking about is purely sending secure messages. So this was touched a bit on last night. Symmetric key XOR cryptography is provably secure as long as the key is kept private and as long as the key is longer than the message. Okay? If you screw up and reuse the key, or if you run out of secure keys and are forced to reuse one, your message is no longer provably secure. If you want to try this out, there's this cool website called projecteuler.net. Problem number 59 explores this problem with a key length of 3 and a message length of 1200. And it's pretty easy to break. So, symmetric key encryption is provably secure, but then it introduces a new problem of how do I send this key to people? How do I know that that key wasn't corrupted in transit? So then you're sort of in the era of secure carrier pigeons or code books or briefcases handcuffed to secret agents riding on trains. So key distribution is clearly an issue. Fortunately, now we live in an era where we have public-private key cryptography, which solves this issue of key distribution. I'll come to this a little bit more later, but basically I generate 2 keys, a private one and a public one. I give everybody my public one, and then I keep the private one to myself. Someone can send me messages. If I have their public key, I can send them messages. I no longer have to send everyone I want to communicate with a code book. So this is widely used online, and the public key, if you've into the math at all, and I'll give a very quick overview. The public key that I tell people has the product of 2 prime numbers in it. And if you can manage to factor this large number into the 2 individual primes, that security is broken. So this factoring problem, it's a hard problem. It is believed to be secure, but it's not proven to be secure. So if you take anything away from this talk, it's that. Public key, a large integer factoring is a hard problem classically, but not as I'll show you on a quantum computer. So I will talk a bit about quantum computing. I will show you the algorithm that breaks public-private key cryptography with this particular method of encryption. And then I'll show you how quantum mechanics turns around and saves the day by giving you a method to securely exchange keys using quantum mechanics. And if you're using this as the outline, just bear in mind I'm going to talk about these in the reverse order, because I think it's easier to understand the key exchange and then talk about the computing. Okay. I've heard RSA mentioned a couple of times during the con so far. So I'm not talking about RSA in any context beyond these 3 guys. Okay, RSA encryption, their algorithm. I'm not talking about anything else. Here's, in a nutshell, how the algorithm works. Okay, and I apologize if you're viewing this later. I'm going to use my laser pointer to guide us through the slides, which is not going to show up on video. But the idea is you choose 2 prime numbers. They can be any two prime numbers. And then you multiply them together. So in this slide, I've chosen prime number 61 times 53 equals this 4-digit number 3233. And this is going to be something called n. We'll call this n. Then I will choose a number d and a number e with a very special relationship. I'm not going to go into that relationship. It gets very mathy. But let's just say that I choose a number d, 2753, number e, 17. And with now these three numbers, I have a public and private key. So the public key will be, the n, the product of these two prime numbers, and this number e. The private key will be this product of two prime numbers and d. So now I have given you the product of two prime numbers. If you are able to factor them, you can read my messages. The encryption protocol is super fast to compute. You basically take a message, raise it to the eth power modulo n, that becomes the encrypted message. So for example, if I have a letter A I wish to send to you, that's ASCII 65. If I perform this operation, that turns it into 2790. Then to decrypt that message, you use the private key. So I take the encrypted message, raise it to the power D, as in dog, modulo n, and that gets the message back. So it's pretty, I'm surprised how straightforward it is, and I'm still a little bit concerned about, we're trusting all our encryption to the product of two prime numbers. But then to reassure myself, I said, okay, how hard is it really to factor numbers? So guys, feel free to shout this out if you know it. What two prime numbers are, go ahed. Thank you. Someone else, can you find the next one? Okay, so with less than 8 bits, we're already stumped. So this is 11 times 13, and this last one is 233 times 241. So if I tell you the prime numbers, you're like, of course. But if you don't know these two prime numbers, it's very hard to get them. Okay? So just to give you an idea of like how hard this problem is, this number that we had no hope of guessing in this talk, this is a 16-bit number, this 56,153. That's a 60-bit number. If you have a computer at hand, you can factor this very, very quickly. It's not that hard. So then I went out to Wikipedia and looked up this page RSA numbers to sort of get an idea of how hard these were to solve. These were publicly put out as a challenge. The challenge ran up through 2009, and then the challenge was stopped because it was, I guess, proven to be hard and no one else was interested. So they closed down the challenge. But from those numbers in 2009, so these are now 2009 speed computers, we're 7 years ahead of that. But a 330-bit key took an hour to factor, all the way up to the largest one that was factored, 768, took an equivalent compute time of 2,000 years. And now typically in production we use, I use 2048 or even 4096-bit keys. So now you're looking at like the compute time is like the age of the universe times 10 to factor this brute force, okay? So that's pretty secure. But we're always in a cryptographic arms race. So let me just lay out some of the key milestones on this timeline. So in 1977 was this RSA algorithm, that's when it was invented. About 8 years later, this guy, David Deutsch, describes the first universal quantum computer. So all purely theoretical, but if you can make any quantum computer, you can then compute anything that any other quantum computer could do. So that gives you sort of the general purpose Turing machine of quantum computing, if you will. In 1994, Peter Shor discovers an algorithm which allows quantum computers to factor prime numbers quickly. And this is when the public really started to take interest in quantum computing as a possibility. In 2014, documents leaked by Snowden confirmed that the NSA is interested in this stuff. So quantum computing has actually been getting a pretty reasonable amount of funding from the US government because the US government either wants to get there first or prove it can't be done. Also in 2014, this is the state of the art that I was able to find on Wikipedia. The number in the earlier slide, 56,153, was factored into 241 times 233 on a 4-qubit quantum computer for the first time. So this is where we are right now. We can factor a 16-bit integer on quantum computers. Stay tuned. I don't know how long it takes to run, but the quantum computer, actually I don't know what it ran on, but a quantum computer is of the type nitrogen atoms in a carbon diamond lattice at liquid nitrogen temperatures, manipulated with lasers and electric fields. So the amount of time it takes to run is probably on the order of minutes once you've set it up. I could be way off base. It may only take seconds. Okay, so I apologize, but I have to give you guys an introduction to quantum mechanics. And in these next couple of slides, there's going to be some very counterintuitive stuff. If you don't follow it, don't worry. It blows a lot of people's minds to this day. So I'll just do my best to talk you through it, and if you have questions, shout them out. So, thought experiment. You guys have heard of this, I'm sure, the Schrodinger's cat experiment. The basic idea is you have a cat, you put it in a box, there's some sort of detector, a hammer, a vial of cyanide, and a radioactive substance, and the radioactive substance, let's find one where, we'll take a small amount of it and say, okay, there's a 50% chance that this radioactive substance decays in an hour. And then the idea is you wait an hour, and then there's a 50% chance that the detector is fired, the hammer is dropped, and the vial of cyanide has been released, and the cat is dead. You monster. Okay, but it's more complicated than that, because if this is a perfectly isolated system, it's not just that there's a 50% chance that the cat is dead, there's also a 50% chance that the cat is alive, and it's even more complicated than that. The cat is in a superposition of alive and dead until you look. And when you look, you collapse the wave function of the cat into either fully dead or fully alive. Okay? So just a hint of the math to come, you can see that the wave function of the cat is 1 over square root of 2 alive and 1 over square root of 2 dead. And you might ask, why isn't 50% alive, 50% dead? Well, the reason is the probability is actually the wave function squared, which allows us to throw some complex numbers in there. If you're not concerned, don't worry too much about that. But now let's take that idea of the cat, which is a macroscopic object. It's ridiculous. You wouldn't ever really want to perform this experiment. It would be incredibly difficult to perform it if you tried. But we can do it with a single atom. So just bear with me. A classical bit, let's call it a coin. A classical bit can be either in a 0 state or a 1 state, so heads or tails. A quantum bit can be in a superposition simultaneously of some fraction tails and some fraction heads, and it will remain in that superposition state until you look. So the analogy is kind of like the spinning coin on a table. It's some combination of both heads and tails. And one thing that makes quantum computing difficult is, like this spinning coin on a table, the qubits will eventually settle. So you must be able to perform your computation fast enough before your quantum computer warms up to room temperature and you lose your calculation. So that's a technical challenge of quantum computing, and one reason why we don't have them yet. I want to talk a little bit about qubits because I think this is really, really cool. And I'm going to step away from the microphone and try to project because I'm going to wave my arms around. But the basic idea is a qubit, it can be in this superposition of 0 and 1 simultaneously. And I mentioned complex numbers a little bit earlier. So without loss of generality, I can transform these complex numbers into basically 2 angles. So instead of a qubit, in this view, a qubit being down is a 1 and up is a 0. But if I'm in a superposition of states and I'm allowed 2 angles, so 0, if I'm half 0 and half 1, my qubit is basically existing somewhere on the surface of the sphere. So my qubit could be pointing left. And then if I measure it, are you 0 or are you 1, it's forced to take its stand. I'm either 0 or I am 1. But it's worse than that. If it's 50% 0 and 50% 1, I also have a complex phase in here. Okay, so that's where the complex number comes in, is there's some other rotation. And so basically I can have a qubit and I can point it at any single point on the sphere, and I can represent an infinite amount of information in a single qubit. And you're like, great, That's awesome. Well, unfortunately, it's not quite so easy because I can only measure it once. And as soon as I measure the qubit, it will collapse into a 0 or a 1. And that's all the information you can get out. So there's a theorem basically that says, you can only read out a 0 or 1. You cannot read out more bits of information than you have qubits. The other thing you might think is, well, why, if I have this bit, why don't I just make a copy of it and read it multiple times? Well, there's another fundamental theorem that says you cannot clone a qubit. So that'll give you guys an idea of sort of what we're dealing with. We can represent infinite information in a single qubit, but we can only read out one bit of information. So how do we build a qubit? You can use any system with 2 or more discrete states. So I can use a photon. I can use polarization. Basically, is it polarized horizontally or is it polarized vertically? I can use a particle, so a spin direction of an atom. Which way is the spin of that particle pointing, up or down? I can use an atom's energy levels. Is it in the ground state or an excited state or some other more complicated state? So there's different physical realizations of a qubit, and these have different advantages and disadvantages. I won't go too much into that unless you guys ask questions. But that was sort of the introduction to quantum mechanics. So now let me show you how you can use that to securely transmit messages. I can breeze through this because you guys know cryptography. Alice and Bob want to communicate. There's an eavesdropper who wants to listen in. Prior to 1970s, we would use a symmetric key, privately transmitted. After the 1970s, we can use these asymmetric keys. But you need a method that's provably secure to distribute your key. So if you have a key, yes, provably secure. But you need a provably secure way to distribute it. So the way we're going to distribute these keys is we're going to use light. And we're going to use polarized light. So polarized light is nothing special. Sorry, I have to step away from the microphone again. I hope you guys can still hear me. I'm going to speak up a bit. So we're actually using polarized light right now to look at this talk. I have the lens from a pair of polarized sunglasses. You can just buy these at any grocery store. If I stick this in the beam, check it out. Apparently, I'm letting the purple light through, and the other light is cooperative. So I didn't realize when I came out here today, but I rotate this 90 degrees, and now the green light is getting through, and the purple light is not. And you keep rotating it. Back and forth. So that's pretty cool. If you do this on a laptop screen, it pretty much goes both on and both right. Apparently, the projector is actually using different colors and different polarizations. I didn't know that. That's kind of cool. So it's really easy to make polarized light. So let's represent bits as polarized light. Let's say if a bit is, or let's say if let me back up a sec. A single particle of light is called a photon, and I will be sending single photons in this protocol. That's a key point. So if my photon is polarized vertically, let's call that a 1. If it's polarized horizontally, let's call that a 0. Makes sense. But now let's also introduce a basis that's rotated by 45 degrees, where if it's polarized diagonally up and to the right, let's call that a 1. If it's polarized down and to the right, let's call that a 0. And so we'll call these two bases the plus basis and the cross basis. So here's a really brief example. Alice wants to send a 1, so she encodes a single bit as a 1, sends it to Bob. Bob measures it in the plus basis. He gets 1 as a result. Similarly, if Alice encodes a 0 and Bob measures in the plus basis, he will find the result as 0. So now what happens if Alice sends a photon encoded as a 1 but encoded in the diagonal basis? Then when Bob measures, it's kind of like the cat. he has a 50% chance of seeing the polarization as a 0 and a 50% chance of seeing the polarization as a 1. And here's the reverse. If Eve sends a 1 and Bob if Eve sends a 1 in the plus basis and Bob measures in the cross basis, the result is a 50% chance of a 0 or a 1. So in order to get 100% message transmission, Bob needs to know what basis Alice sent the message in. However, that's not how we're going to run this experiment. Alice is going to send them randomly. I'll go through this slide slowly, so don't worry. But the idea is Alice is going to send these photons randomly. Bob is going to measure randomly, and then after Alice has sent all the photons that she wants to, only then do they compare notes and say, what basis did you use? So let's break this down. Alice is going to choose from 4 possible values, basically a 0 or a 1, and then a plus or a cross basis to send it in. So we've got this stream of photons going out, and they're encoded as 1100, etc. Then Bob is going to measure, he's going to choose a random basis to measure in. So Bob is going to say, okay, let's, plus, plus, cross, cross, plus, cross, etc. And so Bob has now a sequence of bits, but he doesn't know which ones are right. So then Alice and Bob get on the phone, and there's probably an eavesdropper on the phone. They could do this, anywhere. Publicly, Alice and Bob compare what basis they used, but not the value. So Alice and Bob say, okay, I sent my first photon in the cross basis. Bob says, I measured in the plus basis. Okay, we can't use that one. Then Alice says, okay, I sent my second photon in the vertical basis. Bob says, oh, I also used that basis. I used the plus basis. Okay, that one's good. So Alice and Bob both know that that bit is a 1, but no one else does. Because if someone else got a hold of that photon, Bob didn't get it. So they do this process, and then they have basically a string of bits. They only accept the ones where they were in the same basis, and that becomes their private key, which is now the symmetric key that is provably secure. Now, someone told me, oh, this is a terrible transmission protocol because I'm throwing away half the bits. Like, that's okay. I don't need 1,000,000 bits to tell you a secure message. If I'm answering the question, launch the nukes or not, I only need 1 bit. And this protocol has been run over 100-kilometer distances over fiber cable, and the key generation has been achieved at like several kilobits per second. So you can have a text conversation over this secure protocol. And I've also heard that in like 2010, over shorter fiber optic networks, this is fast enough to do voice and video chat. Okay, so I talked about they form the key from where Bob chose the basis correctly. Then they can also, this is how this protocol is provably secure. They check for eavesdropping. So how do they check for eavesdropping? Let's suppose someone's in the middle of this protocol. So Alice has, she sends a 1. Alice is going to send a 1. Eve is sitting somewhere in the middle of this fiber optic cable that they're using to chat. And she's going to measure Alice's photon. So she measures in the plus basis. She has to choose randomly because it's not revealed ahead of time which basis they're in. So she just happens to choose the same basis. So she measures a plus. She knows the answer is 1. So she needs to generate a new photon and send it on. She can't clone the photon and measure it. So she has to receive it, measure it, create a new photon, send it on. In this case, she got lucky. So Bob is also going to measure in this basis, and Bob will get a 1. So this is sort of classical eavesdropping, right? The eavesdropper received a copy of the message with Bob none the wiser. But as I said, the basis is not announced ahead of time. So what happens in the other situation, where Alice sends a 1, Eve is forced to measure not knowing which state is chosen. She measures in the plus basis. So she gets, suppose, a 1. She has no way of knowing whether this 1 is really like what Eve's or what Alice sent. All she knows is I got a 1, and I got a 1 polarized in this basis. So she sends this on to Bob. Bob measures in the cross basis randomly, and Bob gets now the wrong result. So the chance of this happening is 50% of the time Eve's going to choose the wrong basis, and then 50% of the time Bob's going to get the wrong result as a result of Eve using the wrong basis. So let's just some quick math. Eve gets it wrong 50% of the time. Bob gets Eve's fake message wrong 50% of the time. So that's a 25% error rate. So if you're using this protocol, what you do is you compare a section of the key that you believe to be good. You're not going to use this key to transmit your message, but you're going to use it to check for eavesdropping. And then you say, okay, I measured in plus, I measured in cross, I got a 1, I got a 0. Uh-oh. Keep going. If the key doesn't match up 25% of the time, eavesdropping. It's like, sorry, there's too much eavesdropping detected, I will talk to you later. So this is the same thing in words. There's other ways to compare a key as valid without actually revealing it. You can compare parity of the key to say, okay, well, what parity checksum did you get? Okay, I got the same checksum, we're good. Suppose Eve did get part of the key and you don't know it. Well, then you can just take the key that's good. You can use some hash function to completely scramble it up into a slightly smaller key. And then even if Eve did manage to get a couple of bits of the key here and there, once you've hashed it, she has no information anymore. So this whole protocol, this is provably secure because you can detect eavesdropping. Okay, so now I'm going to switch gears again. If you got your head around that, congratulations. It took me a while. Now I'm going to go a step further and talk about quantum computers. Sorry, there's a caveat here. It's actually a quantum coprocessor. You're probably not going to have a general purpose quantum computer sitting on your desk. However, it's, just like we have, specialized GPUs, we used to have specialized math coprocessors, it's entirely reasonable to have a quantum coprocessor that you're using in combination with a normal computer. So the talk up to this point has been 1 qubit, and now I want to talk about 2 qubits. You need at least 2 qubits to do any kind of interesting computation. So with 2 qubits, you basically have a superposition of 0 and 1. Or I'm sorry, a single qubit is a superposition of 0 and 1. 2 qubits can be a superposition of anything from 0 to 3. And there's some interesting states here that I won't go into, but of course there's the general, like it's equally probable to be anything from 0 to 3. You can also construct special states where it's equally probable, it's 50% likely that those 2 bits are encode a 0, and 50% probable those 2 bits encode a 3. And then you can do some interesting things like teleporting quantum states. Like I can give one of those bits to you in the audience and keep one here, and then I measure it, and I look at mine, I say, okay, mine's a 0. I know that yours is a 0. When you measure yours, yours will be a 0. So we can share information, but unfortunately we can't really communicate faster than the speed of light with this, because I can't control what state you get by measuring my state. Okay, so let's just really briefly, classical computers, there's some theorem in computer science, which I'm not an expert in, but there's some theorem that says classical computers can be built from nothing but NAND gates. So the truth table of a NAND gate is, if the inputs are anything but 1 and 1, the output is 0. So there's an equivalent theorem in for quantum computers that says quantum computers can be built from something called a CNOT operator. It stands for controlled NOT, and just any other single qubit operator. So the CNOT operation works like this. 1 bit, we're just going to pass straight through. It's not going to change. The other bit, we're going to flip if A is 1. So the truth table looks sort of like this. A is 0011. The output is 0011, so A doesn't change. B is 0. Input of B is 0101. Output of B is 0110. So we flipped the B state if the A state was a 1. You can represent this as a matrix if you want. But the one nice thing about this quantum gate is it preserves all of the probabilities. So the probability sums to 1 on the input side of the gate. The probability is going to sum to 1 on the output side of the gate. And you have not made a measurement. So this is something that you can use for computing. This has been experimentally demonstrated. I forgot to put a date on this slide, but if you want to go to this URL and get this paper, it's written for experts, of course, but the bottom line is they demonstrated a quantum entanglement of 2 qubits, basically. This is the one that was done in a diamond lattice with nitrogen substitution. So you have like this lone single electron hanging out that's kind of lonely, and then you can entangle that electron with another electron. So they start with a state that's purely 0, 0, and then they scramble it up and say, okay, now this state is equally probable to be anything from 0 to 3. And then they run this specialized gate on it, and they say, okay, now I'm specially entangled in this state where it's equally probable to be 0 or 3. This is kind of how these things go. And you can tell, this is what they measured. So you can see there are some elements of this matrix where they measured a non-zero value. And that basically shows, hey, this is still very experimental. It's not perfect. So let's talk about Shor's algorithm. This is the algorithm that allows you to use a quantum computer to factor numbers into their primes. This is the one that breaks RSA encryption. Okay, so we'll go through this bit by bit, but here's the big overview. We're going to mathematically transform the factoring problem into a period finding problem, because period finding is much, much easier to do on a quantum computer. So this you do on your desktop. Then you use a quantum computer to find the period using something called a quantum Fourier transform. Does anyone know what a Fourier transform? Okay, a couple people. Okay, awesome. Basically, a Fourier transform takes a spatial measurement into a frequency measurement. So you know those like when you're listening to music and it has those like bar charts that going up and down? That's a Fourier transform, basically. Then so once you know the period, you go back to your classical computer and you use it to factor the number. So we're going to run through a very simple example, which has been done experimentally. And we were going to factor the number 15 into 3 times 5. So, factoring 15. We'll construct a special function, which I don't claim to understand entirely how this works, but it just so happens that this magic function has a period. So let's, how's this go? We need to choose an x so that the greatest common denominator of x and the number we want to factor is 1. So the number we want to factor is 15, so let's choose an x of 7. And then we'll just do this a few times classically so you can see how it goes. So this function of 0 is 7 to the 0th power, which is 1, modulo 15 equals 1. F to the 1 is 7 to the 1, modulo 15 is 7. F to the 2, so 7 squared is 49, modulo 15 is 4. F to the 3, 7 to the 3rd, 200, I don't remember. Modulo 15 is 13. 7 to the 4, modulo 15, we're back to 1, and then this repeats. So you use this function to now change the problem. The problem is no longer factoring 15. The problem is what is the period of the output of this function. I don't claim to be an expert in this. If you don't follow, that's fine. But let's try this out on a quantum computer. So using 8 bits, I want to construct a quantum superposition of the numbers 0 through 255. I need 8 qubits to do this. So here's my state. here's my input state. It has 8 qubits in it. It's a flat superposition of 255, which means if I measure this state, I have an equal probability of getting any result, basically. So now I want to apply this function that I just described to the superposition of input numbers. So let's go ahead and do that. And then we're going to store the results as 4 qubits of output. Okay, so really quickly, we have this input perfect superposition. We're going to hit it with this function, and we're going to get an output, which is basically these numbers repeating, but this is also a superposition of states. Okay, note, at this point, we haven't done our measurement yet, so the input and output states are still coupled. So now what are we going to do? We're going to measure the output state. Boom, we got 1. It doesn't matter what we get, just that we make a measurement. Now, if you remember our Schrodinger's cat picture, this is going to force the quantum computer to collapse into the condition where the output is 1. So, yeah, that's what I just said. And so now the inputs have collapsed into the state where the output is 1, which means the inputs are now a superposition of 0, 4, 8, etc. So we've done a bit of our computation. So the inputs, yeah, so the inputs are now getting us closer to our answer, but don't measure them yet. Because if we measure them now, it will just ruin our computation. So now we're going to apply this Fourier transform. The Fourier transform is going to change position into frequency, and it also goes vice versa. So what we're going to find out is if we hit this number with a Fourier transform, it'll give us the period. Boom. Okay. And it's the discrete Fourier transform, so it's not going to get, it's also going to give multiples of the period. It's just something you have to deal with. But now we can measure the output state and say, what is the period? So we'll measure, let's say we get lucky and we get 64. If we got unlucky and we got 0, it's fast. We'll just set it up and run it again. So the period of the function is then 256 divided by 64 equals 4. Done. We know the period of this function. So now we're done with our quantum computer. We can go back to our classical computer. Here's what we've figured out so far. The period of our function is 4. The number that we're trying to factor is 15. Okay? So here's this cool mathematical relationship. I don't know why this works, but it does. 7 to the power of the period over 2 plus 1, comma, so the greatest common denominator of these two numbers is one of the factors. So 7 to the power 4 over 2 is a half, so 7 to the squared plus 1 is 50, and our n was 15, so greatest common denominator of 50 and 15 is 5. This is something that you can figure out on a classical computer pretty quickly. Flip it around, now we're just going to do the minus 1, so 49 minus 1 is 48, greatest common denominator of 48 and 5 is 3. Ta-da, we have factored 15. Pretty cool, huh? It blows my mind. Okay, but you say, okay, that was a pretty contrived example, Dave. How good is this really? It's actually exponentially better. If you study order of operations, that will scare you a little bit. So classical factoring, follows this order. Anyone familiar with big O notation? It's basically like how many operations does this algorithm take to finish. And there's probably coefficients out front, but computer scientists use this to evaluate the speed of algorithms and come up with better algorithms and win contests and such. So factoring on a classical computer is basically exponential, so the exponential function, and then, it relates to the number of bits in the key. The quantum algorithm, there's no longer an exponential here, it's squared. I apologize, I'm going to hit you with this table to show you how much faster this is. So this is the same table from before, where 16 bits can be factored very fast on a classical computer. This has been achieved on a quantum computer. This is the world record, as far as I know. And this uses a slightly different, well, actually it could be grossly different, but this is a different algorithm than the one I've described. But this is the world record. Factor a 16-bit key on a quantum computer. And this is the table that I showed you before, where a 330-bit key took an hour, and 4096 takes the age of the universe times 1 billion. On a quantum computer, so someone asked me, how fast does this go? I don't know how fast it goes, so I'm just going to use like some units, right? So if you can factor a 330-bit key in 1.1 units on a quantum computer, I'm just applying this formula. So suppose this takes a minute. So I can if this takes a minute, actually, sorry. Let's be even less generous. Let's say this takes an hour to factor on a quantum computer. I can factor a 4096-bit key in 2 weeks. So that brings me to the conclusion, the summary, which basically quantum computers, although they don't exist yet, they can factor numbers exponentially faster than classical computers, which will break much of the encryption that we use on the internet. And just as an aside, someone could record your encrypted communication today and break it once quantum computing is discovered. Food for thought. That being said, there are protocols for provably secure encryption that the fundamental laws of nature say you cannot break this encryption, and I described that to you as well. So that brings me to the end. Thank you so much for listening. If you didn't follow any part of this talk, that's okay. This guy, he's a very famous physicist. He says, I think I can safely say that nobody understands quantum mechanics. So if you didn't understand it, you're in good company. And here's the speaker QR code again, and I'm happy to take questions. Yeah. Guys, you have 15 minutes.